Thank you very much for the kind introduction. Today, I will talk to you guys about, to everyone about the satellite mission, as well, a Keysat, as well as introducing satellite QKD and what quantum key distribution is. And I want to step through a very basic protocol called BB84. And hopefully then by the end of this talk, you will understand how quantum key distribution works, how that can be used to do encrypted keys using a satellite, with the satellite being a trusted node. You can also do this with an untrusted node. You just have to change your source from being a coherent state to an entangled state, because the entanglement guarantees your security. So if your satellite was corrupted, it wouldn't matter. And well, it would matter, you would just know. And then, as I said, I go through the high-level overview of this Keysat mission. So a lot of people, they like to know how I became a scientist. So always asking why, that's definitely the first start. Always ask why. Always ask why. And then go to school. So I went to the University of Calgary in Canada for my undergrad, and I studied physics and did a Bachelor's of Science. Then I moved across the world to Australia, and you can see in this picture, the beautiful city of Canberra. And I studied at the University of New South Wales and did my PhD in electrical engineering. Often they put laser physicists in electrical engineering departments, as they should, because when we start to do these experiments, yes, we still need to understand quantum physics, but as soon as the light has turned into an electronic signal, everything is electronics. Your amplifiers, your detectors, your signal analysis, your filtering, everything is electronics. So really, it's the harmonious combination. When you become a quantum physicist now, a quantum optical physicist now, it's this combination of physics, optics, and RF engineering. And then I moved back to Canada, and I went to do a postdoctoral fellowship at IQC, so the Institute for Quantum Computing at the University of Waterloo. And I was there with, so I joined the group with Thomas Yenavine. So he's my current PI, and I'm still with this group, but now actually located in Calgary, which is why it's 6 a.m., not 8 a.m. And I'm a research associate and working on the Keysat science team. So my prof, Thomas Yenavine, he's the PI for the science team, and I'm helping coordinate all of our collaborators, as well as working on the research side. Doing some link analysis for Keysat, for example. Alrighty. So since it could be anyone watching this right now, so I'm going to start a little bit broad and then go more narrow. So in a very, very basic level, what's a quantum physicist? What's quantum physics, right? So it's the study of the tiny. It's the study of atoms, as you can see here, like, for example, the Bohr model of the atom. It's the understanding of how bonds work in chemicals. We can understand the orbitals of electron orbitals, so that we can understand why chemicals bond the way they do. And what's really cool is that the tiny of our universe looks way different and acts a lot differently than the macro of our universe. And that's something that we're always struggling to reconcile, right? So we understand how planets move, and we understand how particles move. But then if you try to understand a black hole, where you take the masses of the universe and then combine them into a tiny little compact space with singularity, things break down, right? But for now, let's just think about the quantum side. So if you were to focus on a piece of chalk, actually, this bottom picture here on the bottom right, that's what chalk looks like when you zoom in. So obviously, the quantum world is a lot different than the world you see with your eyes. And now I said I'm also an optical physicist, right? So what does that mean? Well, I use light to study quantum phenomenon and to explore quantum phenomenon. And so at a very basic level, light is an electromagnetic wave. I know a lot of you already know this, but like I said, there could be some non-experts listening. And a very, very important concept that I want everyone to understand before we continue, because polarization is so important in this discussion, is what is polarization? So you have light, right? And light is this electromagnetic wave. What does that mean? It has an electric field and a magnetic field, as shown in this picture in the top right. And the polarization of light, it's just a label, okay? Like how color is a label, like, red light, green light, for example. So polarization is just another label. And so we pick a direction. We pick to align polarization to the electric field. And so whatever direction the electric field is oscillating in, that is the polarization of the light. And you might have seen this before. Light can do very interesting things. And when we start to examine it on the particle scale, so light can act like a wave or like a particle, with the duality of that. And so the Young double slit experiment was an excellent example of that. Just wanted to show that. Okay. So that's the very, very basic introduction of that. Yes, I know. Okay. So what we're going to talk about now, we're going to focus on quantum key distribution. So why do we even need quantum key distribution? What is QKD? So the importance of this is it is security. QKD is all about security. And it's because the security of QKD, securing your information nowadays, right? It's usually we use public key encryption, okay? Public key distribution. Public keys are reliant on, the security of a public key is reliant on being able to not solve very difficult computational problems. So factorizing a very large number into two numbers, that's a hard problem for a classical computer to do. A quantum computer can do it like that. So we need to have a replacement for that type of security. So quantum key distribution is not based on, the security of it is not based on the computational hardness of solving a mathematical problem, but rather it is based on the physical processes that are not vulnerable to a quantum computer or any computer. It is always going to be secure. If it's secure today, it'll be always secure tomorrow and in the future. So that's a property that's called forward security. So if an encryption key that's generated using QKD is secure today, it'll remain secure against all advances in computation. And as I said before, we have a particle. We can break up light and we can see it as waves or as particles. If we say it's as particles, a photon is a particle of light, and a photon carries one unit of information, and we call that a qubit because it's a quantum bit. Now it's very important. One of the key reasons why QKD is so secure is because quantum information can be transferred, but can never be copied. Okay, it can never be copied. It's a cloning theorem. And also measurements disturb the state or the system. So every time someone tries to listen in, tries to tap into your phone call, they disturb the system. That raises an alarm. You know there's an eavesdropper. You stop the call. Okay. So one of the projects that I worked on with Thomas was to look at how real world effects in free space quantum key distribution communication, say between two ships on the ocean, like in this picture, except of course the ocean is not being shown. So imagine there's two ships on the ocean. They want to use a laser to communicate, right? But that laser has to travel through free space. It has to travel through the air. That means it has to travel over the ocean, right? Because it's a horizontal channel. There is a lot of atmospheric turbulence over an ocean, especially over large bodies of heat mass, right? The air is very turbulent. So how does that affect your light? How does that affect your ability to communicate? Okay, so we can study that in the lab so that we can know how the vulnerabilities are of these systems in real life. So if you were to take a picture of the laser before the turbulence, it would look like a Gaussian beam. And then if you were to take a picture of the light after turbulence, it would look very messy, right? And so I was using a spatial light modulator in this experiment to emulate atmospheric turbulence in the lab, and then testing how that affects our QKD protocol. Now, the really cool thing is that not only so remember Alice and Bob are the two parties trying to communicate. So not only are Alice and Bob's signals being disturbed, but also Eve the eavesdropper. So Eve the eavesdropper, the evil person trying to listen in, they are also going to have their beam affected. So the fact that A, their beam gets affected, and B, a hacker can be detected in the channel because measurement disturbs the system, these are the ways that we can keep QKD from being vulnerable. So there's a lot of countries. This is just a very brief snapshot, and it's even from 3 years ago, so this is already out of date, about how many different countries there are launching satellites, getting involved, creating ground stations. It's literally the quantum space race right now. And so you can see in this part of the picture here that IQC, where I work, Institute for Quantum Computing, we've done two. There's the current mission, the Keysight mission, which will be launching in about 2 years, less than 2 years. And then the first mission we did as a demonstration mission involved a plane. So we did, and what's interesting about this picture is that the person that drew it actually took the detail of showing where's the uplinks and where's the downlinks. So if the source is on the satellite, then it's a narrow beam at the top. And if the source and the receiver's on the ground, and if the source is on the ground, then it's narrow at the bottom. So like for Keysight, for example, we have our receiver on the satellite, and all of the sources will be on the ground. Whereas for some of these other missions, for example, on the Nicias mission for China, their sources are on the satellite, and then all of the receivers are on the ground. And so there's advantages and disadvantages to doing an uplink or a downlink configuration, which I'm happy to discuss. But for now, I just want to go back. And by the way, I wanted to make this somewhat informal. So if there are any questions, please, you can always ask something, because I'd rather not lose everyone at the start. But I will keep going. Okay. So I want to step through this protocol, QKD protocol, first presented by Charles Bennett and Gilles Broussard. And so it's called the BB84 protocol. And it's basically how do we use light, and in this case, polarization, to create a code. So if you remember, like when you were in school, right? I mean, you're all probably still in school, but when you were like little and you wanted to talk with your friends, you didn't want your teacher to find to read the note. And if your teacher found the note, you didn't want it to make any sense to the teacher, right? So you would make, up a code, right? And you and your friend, maybe A becomes H and B becomes G and C becomes, J, for example, right? This mapping of letters to different letters, that is your encryption code. Okay, so if you have that encryption code and your friend has that encryption code, and you use that encryption code to change your message, I want to get ice cream, you want to change that message to something else, right? Using that code, now it's just gibberish. So when your teacher gets it, it's like, what the heck is this? That's what we're trying to do, right? But we're not trying to make the message right now. We're just trying to make that code. We're just trying to make the mapping, okay? And so just to make up that between Alice and Bob, make up that special code so that we can use that code to then encrypt the message, okay? So to do that, we use each photon carries one qubit of information, as I said, and we're going to use polarization. So we're going to assign a bit value to each polarization state. So one becomes vertical polarization, right? Horizontal polarization is going to be a 0. And then in this picture, each little arrow is representing a photon traveling from Alice to Bob. Okay, so Bob is the receiver, Alice is the sender. And I think everybody understands polarization now. So next, next slide. Okay, and then we also, we need to, because of the way the protocol works, the way the math works, the way, and I didn't show that math here because this is a general discussion, but I can point you to the right references to show you this. You have to have two what's called bases, okay? So we have what's called the rectilinear or just horizontal vertical basis, right? And then the diagonal basis, this diagonal, anti-diagonal basis. And it's important that the two bases, right, are not orthogonal. So vertical light is not orthogonal to diagonal light. It's 45 degrees off, right? Vertical and horizontal are orthogonal. Good, we need that pair. And we need diagonal and anti-diagonal to be orthogonal. Good, we have that pair. But then the two bases cannot, okay? And then we assign the zeros and ones. Okay. So first step in this protocol, once we've done those labeling, right, is we need a random number generator, preferably a quantum random number generator, because Alice has to choose which state to send to the receiver. So there needs to be, if there is any pattern to her choices, then that is a vulnerability. So you need that's a security vulnerability, because then a hacker, if they were listening in just a little bit, just enough not to raise an alarm, but enough to learn something. If there is a pattern in your light, they can learn something. It's a vulnerability. So you do not want an eavesdropper to be able to hear anything. And if they do hear something, no patterns, right? So you use a random number generator to choose which polarization state to send. H, V, D, A. You got 4 choices. So you have this switch. We're good. Then Bob has, he's a receiver. So he has to measure either in one basis or the other. So Bob either measures in HV basis, shown in this detector, or the AD basis. So the light comes in. Again, there's some either an optic or like a passive optics, like a beam splitter, or active optics, like a switch. And Bob chooses randomly which basis to measure in. And again, this needs to be inherently random, and it needs to be a different random set of random numbers than what Alice used. So in QKD protocols, some people, they seem to glance over the fact that we really need quantum random number generators as well for these protocols to work properly. So then we have our detectors, and these detectors, they're just beam splitters, and they are just going to measure with photodetectors whether there is a photon or not. So if there's a horizontal, let's take the first one here. So this is a diagonal, this little green arrow is a diagonal photon, so it'll come in. And then if this random number switch is saying, okay, go up to the AD detector set, then if everything works properly, the efficiencies are good, the beam splitter, the polarizing beam splitter separates the D from the A properly, then the D detector should click and Bob should get a 1. So what I want to do is step through this protocol and see what happens. So if Alice was to start off by sending this diagonal for a 0, right? But then if Bob sets up, because it's random, so if Bob ends up choosing quote unquote the wrong basis to measure in, because Bob doesn't know what basis Alice was sending in, and that's on purpose. So sometimes you're going to throw away some of these signals if there's not, if they choose different bases randomly, then you just have to throw away those signals. But remember, this is not the message. This is just trying to build up the key. So you're allowed to throw stuff away. It's not throwing away the message. You're just building up a key. So if Bob measures an H, and because if you send horizontal light, right? Sorry, if you send diagonal light into this horizontal vertical detector, there's a 50-50 chance that that horizontal photon, or that diagonal photon will click either H or V, because diagonal light is 50% horizontal, 50% vertical, right? So this is why you throw it away. It's a random result. You're supposed to be getting a 0, but Bob, if Bob measures in the wrong basis, the result could be 0 or 1. And so in this case, sometimes you might get lucky and you get the right one, but you don't know. That's the point. So every time the basis is wrong between them, you have to throw out that bit. So this one gets thrown out because it's in the wrong basis. So then if we do another one, so now again, Alice sends a different diagonal one, but this time Bob measures in the diagonal basis. So if that happens and there's no loss, right? Then it should measure the correct photon, and so you keep that bit. So now we have one for our bit, and then you do it again. You keep going, and every time the bases match, you keep the bit. Every time the bases don't match, you throw it out. So now you're probably going to ask me, well, how do you know when the bases match or don't match? Because after Alice, because you don't know when you're live, when you're real time. So when Alice is sending this light to Bob, right, you're building up this key, these signals, and then after that's been built up, there's a reconciliation phase in the stage, and that's when Alice and Bob announce which bases they sent or measured in, and so then that reconciliation sifts out the wrongs. So, well, what about Eve? Because Eve's going to make mistakes too. And if Eve tries to make a measurement of the light and chooses the wrong basis, then she's basically introducing randomness every time she does that. Randomness, loss, that causes errors. Errors means we find Eve. So as I said before, and we have this real life situation where you're trying to do QKD between the two boats, right? If Eve is trying to hack in and tries to tip off some of the signal, does the wrong measurement, introduces noise, raises the alarm, because measurement disturbs the system. Cool. So that was the BB84 protocol, and you can use that to distribute keys using a satellite. So I'm going to go through now I'm going to go through the mission, but just really quick, what happens is that so in our case, for example, right, we've got our sources on the ground. So we have Alice on the ground, we have Bob on the satellite. So if we wanted to exchange a key between Calgary and Waterloo, which is very possible, it's one of the things we will be doing, because there is going to be a ground station in Calgary, and there will be a ground station, one of the main ground stations at IQC in Waterloo. So what will happen is there'll be a flyover, and the Keysat will first link with Calgary, for example. And so Alice and Bob, right, will start their key generation. And then in this situation, the satellite is a trusted node. So the satellite will have that key that's been generated with Calgary. Then the satellite will go over top of Waterloo, right? And of course, because of the paths of the way satellites track, it might take a few passes over the night before it's back over Waterloo, depending on how it is, right? So once it's over Waterloo, satellite makes the link with Waterloo. So key A was with Calgary. Key B is with Waterloo. So now Calgary has a key, right? Waterloo has a key. They're different keys. They were both made with the satellite. So now what do? So you XOR, the satellite has the two keys. So you XOR the two keys, you bitwise XOR the two keys together, the operation. And then the satellite announces the XOR of the two keys. Now I want my whiteboard. One sec. Just really quick. So key A, no, I can't see that. Okay, so we got, I don't know if you can see this. key A XOR key B equals key C. No, you can't see that. Yeah. Okay. So then the satellite announces the XOR of that. So then, if Calgary knows key A and Waterloo knows key B, so then when the satellite announces key C, they can do an XOR with that announcement and the key they have, and they get back one of the other keys. So hopefully you can see that. All right. So go back. So in a very general sense, that would be how we would make a key between two ground stations using the satellite as a trusted node. And it's called a trusted node because it knew both keys all the time, right? You can have untrusted node where instead of using coherent states, polarization states, instead of using coherent states to send the light, you use entangled states. Entanglement guarantees the security. So, there's other ways to get around it so you don't have to have a trusted node. I wanted to show this picture because before we could get to the satellite mission, we had to do a lot of proof of principle demonstrations. And so this is actually a picture of our QKD receiver. You can see the orange fibers, the orange multimode fibers connected to the optics to collect the light. This is mounted on the back of a truck and was literally driven along one of the streets so that it was a 1 kilometer link from our transmitter that was on campus at the University of Waterloo. And this was a successful experiment. It proved that the receiver has the ability to create a QKD link over free space. And a lot of this work then went into, once the proof principle demonstrations were done, into miniaturization of the optics. So you can see, like, there's no way we could put a receiver like this big on a satellite. It's just not possible. You have to miniaturize this and use space ready hardware and things like this, right? So some of our next stages of this work were to miniaturize so you can see in the bottom left here, that's the actual receiver once it's been shrunk down and everything removed. So it's very compact, and the electronics to run the system. So after we did the truck demonstration, the next thing was to do a much longer free space link. So we put actually the receiver into this plane. So we did with the NRC, there was a collaboration in 2017. And the group flew the plane, the receiver was up there. These are pictures of the ground station. And you can see that in this picture here on the left, the streak is the plane flying overhead as we were linking to it. And so this was also successful, which led into the Keysight mission. So what is the Keysight mission? So in 2017, the Canadian government announced funding for 5 years for this quantum encryption and science satellite mission. And as I said, it's based on polarization states. So we are encoding information using polarization of light and using lasers and a ground station to generate this free space link and to allow us to do QKD. And then in 2000, as I said, it was 2016. That was when the link was demonstrated with the ground at Smith Falls in Ontario. And then in late 2017, that's when the Keysight mission was really starting to go ahead, and that Thomas Yanavine was named the Keysight PI. So this is just the snapshot of what our Canadian science team looked like, but it's already been evolving. We have at least 12 institutions across Canada, and then about 12 institutions around the world. And by the way, if anyone is listening, watching, and you would like to contact us about potentially having collaboration, please do. We would love to have ground stations in Africa. That would be amazing. So one of the goals of this project is to have, is to study different geographical locations with different climates, with different ground station light pollution conditions, so that we can do, so this is a demonstration mission, right? The satellite mission is a demonstration mission. So we're going to be trying out different quantum sources. That's one of the reasons why we have so many collaborators, because one person could be, we want to be able to link various quantum sources like atomic memories, for example. I think I have a, no, never mind. Yeah, so we want to link lots of different quantum sources, from quantum dots, entangled sources, do a link from the satellite to, say, an atomic memory, but the atomic memory might work at a different color, a different wavelength than the Keysight link. So we want to also work on transducers, so wavelength converters. And last year, myself and Thomas, we hosted this Keysight Canadian Science Team Kickoff Meeting. It was all virtual, and I'm very happy to say it was very successful. We had about 40 researchers and PIs on the call, each representing their institution across Canada, giving presentations on what they can bring to the what science activities they would like to do with the mission. And so my job is to help coordinate all those things, as well as working on the actual science part. So as I said before, this picture was very clever in that they wanted to show uplink versus downlink, and so I've just tried to highlight that with my own little extras here, because what's time? Oh, yeah, I've been talking a lot longer than I thought. All right. I'm not going to talk about that. We're just going to go to this one. So yeah, the quantum uplink channel, as I said, is what we're going to be doing, because the quantum receiver is on the satellite, and it is a 4-state polarization analyzer. And the receiver passband is between 780 and 795 nanometers. So if you would like to talk to the satellite, that is the wavelength that is acceptable. Keysight will link to many multiple quantum sources, as I mentioned, to test various ground to space links. So we want to link a ground fiber network potentially to Keysight. So if there was a metropolitan city, for example, Calgary has demonstrated and does have a fiber network in the city that has demonstrated teleportation already a few years ago from the researchers at the University of Calgary, who are also on our science team. So linking the satellite to metropolitan fiber networks is also a very ambitious goal, but important, because this is the stepping stones to making a global quantum internet. If we want to connect quantum devices around the world, it's not possible to do that quantumly using, that's not a word, using fiber optics. Fiber optics, you have a limit of 200 to 300 kilometers to send quantum signals. We have to use free space. But free space has its own challenges, as we all understand, turbulence, things like this. And optical signals are the best for sending in free space. Whereas other devices, for example, atomic memories, quantum computers, they can be working on a different wavelength. They can be working on RF scale, microwave scale. So that's why I was mentioning transducers are also very important technology in building up this network. So yes, the overall goal is to demonstrate quantum links and QKD in Canada, and also to study things, as I mentioned before, about like entanglement in relativistic settings, trying to push this envelope of finding that the physics between the macro and the micro. So when we start to push the velocity scales, we start to push the the link distances. That's where we start to test, is entanglement a quantum, we know it's a quantum phenomenon, but does it have length limitations, or is it truly everywhere at all times? Was Einstein right? Is it really spooky action at a distance, right? So we actually made this QKD demonstrator platform as part of a project with Xelitis. You can see our time tagger, this blue box at the back behind Alice. That's the actual time tagger that is running the system. So this is a real QKD system. It's using an LED source actually to generate these polarization photons. We have switches. So Alice chooses A, B, D, A, these buttons here. You have Eve, the red box in the middle. So if she wants to attack, you turn her on. And then Bob, you choose, do you want to measure an HB or DA? And yes, it's a very successful proof of principle demo that has proper single photon detectors and a proper time tagger, which makes the statistics actually real QKD. Okay. Anyways, thank you very much. That's everything.
Wow, thank you so much, Katanya, for such a talk. And I liked the part where you mentioned the possibility to collaborate with ground stations in Africa. And
it's my job to talk to you about that.
we love that because we're trying to think about quantum tech in terms of opportunities and challenges for Africa. So thank you very much for that. It's
Yes.
proving useful.
Fantastic. Yes.
Let's see what's happening in the chat box and see. Okay, so thank you so much for the amazing presentation. I've got two questions. Why does international collaboration matter for science and quantum? Just to motivate, especially what we're just talking about now, where you need ground stations across the world to look at how we can build the quantum internet in the future.
The reason for collaboration?
Yes, as in why would international collaboration matter? Because sometimes when we talk to people in Africa, I guess sometimes people think it's far-fetched. We may not be working at the high level where you are working at the moment, and the scientists in the continent may feel timid to participate. So how would you respond to that? Why is it important for them to open up for international collaboration?
100%. Yeah. Okay, so I'll put on my Keysight hat and answer the question, and then I want to put on my I'm a human being who's a scientist and answer the question. So it's Keysight, because not everyone is an expert on everything. So even if you think that maybe you're, not the top of your game, you are. There's a reason you want to talk to me. So if you have anything, I'm sure it's something that's going to build, and you're going to learn. It's the exchange of information. It's the exchange of becoming involved. The amounts that we learn when we work together is so much more than when we work independently. I mean, and that's when I'm going to transition to I'm a person and not take off the Keysight hat. I'm a scientist that I think everyone on this planet deserves to understand what they want to understand. And if you want to learn, how are you going to learn in isolation? So one of the things that I want to do personally is make it so that we can have this global internet, this global network that is A, secure, and B, available to everyone. We have 8 billion people almost on this planet, and how many of those people actually have the internet? How many of those people have that opportunity to watch this talk and learn these things? And we're all humans, so that's why I think you should collaborate.
Okay, sounds good. If you want to also ask questions to Katanya, please unmute and come through. I'm just looking at the chats and trying to address those questions found there. Any word for women interested in quantum?
um,
Hello, Katanya, did you hear me?
No, you cut off. I heard women interested in quantum. Here, I opened up the chat so I can.
Okay, sorry for that. So
That's it. Which one?
it's okay. So you can take it through from the chat then.
Yeah. So
Just try to
any
take the ones
words
that you
for
see in the
women
chat. That's
interested in
okay.
quantum? Sorry. What?
Oh, so sorry, I was saying you can just read through the chats as well. I guess my network is a bit challenging.
Yeah, no, I can hear you. It's all good. Yes. So any word for women interested in quantum, 100%. So it doesn't matter what your gender is. We all have brains. Some people's brains like science. Some people's brains don't like science. If you like science and you want to do it, please do it. Like seriously, we're all just people. And so women interested in science, I mean, the way I got into it, I was very fortunate. I went to the University of Calgary and I happened to find a professor who wanted to mentor me because they wanted to mentor people. So I would find a mentor. I can help you find a mentor. I might be able to be your mentor. So yes, and the other thing I would say is for women in science in general, there has never been a better time to be alive and be a woman in science. Because if I was born 300 years ago, I don't think I would have had the same opportunities as I have now. And I fully acknowledge the fact that I live a very privileged life living in North America, and that's a whole other situation. But women in science, just find a mentor, follow your heart, and believe that you can do it is the other thing. Okay, so why did you start having interest in STEAM and STEM? Because of what I said. I'm a very strong believer that anyone can understand anything, and as long as it's taught to them in a way that they can understand. If you speak in a language, if you use terms, if you can communicate with someone, you can make them understand anything, right? And this knowledge, this is the fundamental knowledge of our universe. Like, how do we all not just know this? It's like this is quite important, I think. So I got interested into this outreach side because I think that yeah, grade six students, for example, they now understand what an atom is and what light is and what entanglement is. And I think if we start to explain these concepts at a younger age and we start to introduce science to the general population at a younger age, it'll just open up more opportunities for everyone. Because if you never even knew, you could be a physicist, then why? If you didn't even know you could be a physicist, you will never become a physicist, right? Like, okay, so that's why I have an interest in that. And yes, I have some videos. Thank you. One question: what is your view on QKD versus quantum secure classical encryption? Sorry, I'll read that properly. So what is your view on QKD versus quantum secure classical encryption? I know what you're talking about, especially given that classical infrastructure is so pervasive. Yes, so there is a transition that we're doing right now. There's several companies and academics working in this field where we don't have quantum key distribution to deploy immediately now, but we do want to start to have better security than the public key I was talking about before. And so people have started to make these quantum secure classical encryption codes. So it's like the transition step, right? It's better than doing nothing, but it's not QKD yet. So my view on that is that we need to continue to improve security, and that quantum secure protocols and post-quantum protocols are the way to go as we build up the QKD network itself. Yeah. I hope that answers the question. I'm not really sure. Cool. Hey, I survived. Yes. Now I know I can give talks at 6 in the morning. This is good to know.
Sounds good. Sounds good. Let's see. So you managed to go through them all, did you?
Well, yeah, so there was why should companies, governments, and students pay attention to quantum? Yeah, so I missed that one. So everyone right now, right, they are around the world, like I said, there's a quantum space race. Why? Well, it's like in the 1950s and the 1960s when we had the computers and 70s and 80s when it was all taking off, right? Like quantum technologies is literally the new IT. So in the next 5, 10, 15 years, quantum, like I'm involved in this as well. Quantum technology is going to be pervasive in all of these fields: medical, security, financial, bank, everything can benefit from. Yeah, that's a very broad statement, of course, but I mean, we've seen how quantum technology can improve sensors. It can improve search algorithms. It can improve communication. So when I say it'll improve everything, it's a very broad statement, but this is why companies, governments, and students should be paying attention to quantum. It's because this is literally the next stage of our technologies as a society. So yeah.
Sounds good, Katanya. Thank you very much for that. Thank you very much. We learned a lot, and we really appreciate your early morning, rising in the early morning to be with us. And if you are free, let's go for the cocktail. We usually host a cocktail where we come together and perhaps have a chance to talk one-on-one and build closer relationships and talk about things that matter between us as individuals. And if you are free to join that, we'll be very happy. People would want to talk to you further. And,
yeah, I can definitely join for a bit.
Sure. So we shared the link in the chat box to join the cocktail. And
okay.
Sure. So you can follow that and we can meet over there. Thank you everyone for joining. Thank you. We had people, Terrell from the US and many other people from across the world. I've posted this widely, so I don't know where people are from, but I know that we've tried to capture almost everybody whom we could reach to come through for the meeting, and I think they enjoyed and benefited a lot. And on also the answers for the questions that we're asking, I think those were very critical. Those are very critical questions we always come across as we talk about quantum out there. And thank you very much for giving us a starting point. It leaves us to end this meeting and to catch up on the cocktail, and let's keep this conversation going. And I hope we have you again coming to be with us in future to talk about many of the things that you're working on and share the progress as well.
Thank you so much for the opportunity to speak.
My pleasure, Katanya, and let's meet on the cocktail. Cheers. Thank you, everyone.